So today I want to talk to you about NISAR, which is a fantastic new space mission that NASA is going to be launching this year, this April actually. So it's just a few weeks away before this mission is going to go up into space. I will talk to you about how in many ways this mission is a groundbreaking mission. It's one of the most capable missions of its kind that was ever launched. It's going to create more data than any other space missions before it. And it's going to serve a number of science and applications communities more than any other mission, I think, has fed in the past. But more importantly, Alaska and Alaskans have had a very important impact on this mission, have contributed to this mission, and will help this mission succeed in the future. So I will talk about that as well. So I was asked, which is kind of nice, so if you didn't listen to Wade, you can listen to it one more time. I was asked to add a slide in that says, oops, my remote is not working. Oh, okay. I was asked to add in a slide. It was like, who's that Franz guy anyway? So I added one in. So I grew up in Germany, and as Wade said, I grew up in a small town in southern Germany, and will fly right to the compound where I grew up, sort of the farm of a million roofs, as you will see. So all of these roofs belong to us. I grew up among, as he said, cows and chickens. That's sort of the dumbest cow picture I could find on my phone. This house is actually a multi-generational house, so I was very blessed to grow up with my grandparents, my parents, and all of our siblings under the same roof, which is not something that happens too much anymore. I moved to Munich to get my degree, as Wade mentioned. I got a degree in engineering, geodetic engineering for the master's, and then engineering for the PhD. The campus of the university is in the middle of Munich. If you have never been to Munich, you should go and visit. It's a beautiful place. There are lots of museums right around campus. In 2004, I then started working for the German Aerospace Center, as Wade mentioned, which is very close by to Munich. I worked in this building, which is the Remote Sensing Technology Institute, and worked on this mission called TerraSAR. Very fantastic mission, which was launched in 2007, which incidentally is the same year when I moved finally to Alaska, and joined the university here at the Geophysical Institute. And I'm going to just turn the laser pointer on. And so here, as Wade mentioned, I like the outdoors. I have my ATV that I like a lot, and I'm not sure if you can see this in the last picture. Apparently, I'm missing the Bavarian pretzels. I'm not sure if you can see this here. I have no idea what the context of this photo is, but I scrolled through my phone earlier today and found it, and so I thought it fits the story, so I added it in here. I have no idea who took that. So going back to NISAR is a mission that was built specifically to monitor how the world is changing, dynamic signals on the planet. And how dynamic the world is, nobody knows better than us in Alaska. If you were here just a few weeks ago, you know, we saw a building shake after the earthquake in Sitka. And so we understand dynamic signals. Across the state, we have lots of things going on. In the north, we have sea ice. That's very important for us, for transportation, to preserve the coast, for transportation out to installations in the ocean. It affects our shipping lanes, all of these important tasks. We have coastal erosion. That's a huge thing in Alaska. We had to relocate several villages over the last few years as the coastline is receding. In the interior, we know that we are affected by permafrost. Permafrost, as it's changing, is affecting very strongly the hydrology in the region, but it's also of much more hands-on impacts. It affects our infrastructure, our housing, the stability of roads, etc. And of course, wildfires, we all know, are affecting air quality, but they're also changing the ecosystems around us. And then in the south, we have lots of dynamic things going on. We have a subduction zone that's full of volcanoes. I think we have 40 or so active volcanoes around the state. We had some of the largest earthquakes ever recorded happened in Alaska, including a fairly big one just a few years ago, 2018 in Anchorage. So lots of dynamic things going on the planet. And NISAR is a mission that is built for monitoring all of these signals. And so if we want to really map and understand and try to model all of the things that are going on the planet, we need data that can monitor the entire planet all the time. We need data from space. We need so-called Earth observation data, images, data sets from space. And so my story today is talking about one of those missions, NISAR, which is quite a marvelous mission. I'll talk to you about what makes that mission so special and better than all the other ones that are out there right now, how it works, and what kind of science it will support. And as I mentioned, I will talk about the role of Alaska and Alaskans in this mission. So Earth observation is the key for us to understand, monitor, describe all of these dynamic things that are going on the planet. And of course, Earth observation has been around for a very long time. We have been monitoring the planet with various sensors for a very long time. This example here shows a time series of Landsat data sets. I'm not sure if this is playing. Oh, it is. And so this shows from 1970 to today, the main signals you see here is the growth of Las Vegas. This is in the area of Las Vegas. But if you focus over here also, you see how the lake levels in Lake Mead have decreased over the years through the amount of water that Las Vegas is using and through just reduced precipitation there. So this shows you how important these data sets can be on understanding these dynamic signals. But these systems that we had used for many years, they have two main disadvantages. One of them is they don't work when it's dark. And it turns out it's dark a lot, especially if you live in the Arctic. So you are here, located up here. And so it's a big handicap if you want to monitor something continuously, if half the time you can't see the ground. Even when it's daylight, many of these missions have the problem that cloud cover is in the way, and we can't actually see the ground. This data set here is a 30-year average of cloud cover around the planet. The places that are shown in sort of the whitish colors, those are heavily cloud covered. And you can see that with the exception of the big desert regions, which includes California in this case, and Atacama deserts, and Gobi, and the Sahara, everything else is fairly consistently cloud covered. The percentage of cloud cover is very high, which means we miss out of more chances to describe these dynamic things that are going on the planet. So what we are using and what NISAR is using is a concept called radar. So we are using microwave signals from space to sense the planet. And that gives two advantages. It actually defeats both of those problems that I talked to you about earlier. The microwave spectrum, which is over here where you see this box, first of all, it is the atmosphere is very transparent in the microwave frequency range. So when you look at this sort of brownish color in the background, this shows you the opacity of the atmosphere. In places where you see lots of brown, it means signals that come from the outside cannot penetrate through the atmosphere to the ground. So we need a window where the opacity is low or the transmissivity is high. The optical window is here, that's one of them, and then the radar window is out here. A very wide, fairly unaffected window. And the advantage of radar is that radar can penetrate clouds and can penetrate rain. So during daylight already, we can see the ground all the time. Additionally, radar is an active sensor. So in a radar satellite actually actively transmits signals from the satellite to the ground. So we don't need an external source. We don't need sunlight in order to illuminate the ground. We do it ourselves. And this also takes care of the nighttime problem. And for radar, basically, there is never any night on the planet. So radar senses these days, those so-called imaging radars. We often call them SARs, synthetic aperture radars. I'll get to that in a little bit. Those are one of very few true 24/7 capable instruments. They can monitor things all the time. And the example that you see on this slide is an important one, or shows the benefits of this. This is a site called Madre de Dios, which is in the Peruvian rainforest. The site is interesting for two reasons. One, it is very, very cloud covered. It's one of the most cloud covered places on the planet. A colleague of mine from the University of Alabama, Huntsville, did a study to see how many optical data sets catch this area cloud free, and there's one a year. So you get a single shot per year where you actually see the ground. Radar can see this ground every 12 days. Additionally, this is a very dynamic place. When you focus on this bottom right corner down here, you see sort of this black feature that's growing over time. This is a deforestation site. A lot of this deforestation that's happening here is illegal. It's folks that are gold mining illegally in the area. And radar, in this case, is the only sensor that was able to sort of track this activity in this site. And so there are many applications like this where cloud cover, et cetera, hampers other sensors, and radar is important to understand the dynamics that are going on. So radar has been around for a while, but I'm going to claim in the next few slides or in this talk that NISAR, which is a new mission that's coming this year, is going to be even better than what we have currently in space. So NISAR will go up in April of this year, just a few weeks from now, so we're all very, very excited. It's going to launch from a location in India. NISAR is a collaboration between NASA and the Indian Space Research Organization, ISRO. It's a very tight joint development. The mission was built by those two agencies throughout. And the launch out of India is testament of this collaboration. It's going to be launched by a launch vehicle, an Indian launch vehicle called GSLV Mark II. And so this is what this vehicle looks like. It's a two-stage rocket. You see here how the first stage is getting us into orbit. The second stage then lifts the instrument close to the science orbit. Then the instrument is separating, and that's where you see NISAR for the first time. So this is here the NISAR instrument. Sorry, I'm going to walk out of the picture here for a sec. I'm going to turn you around. Hi, guys. So NISAR is a radar instrument. The radar transmitters are actually here on top. But it reflects radar down to the ground with a large reflector. That's a 12-meter reflector that's stored in this little canister. NISAR, the reflector is going to get unfolded over a sequence of steps that will take about 10 days to unfold. So it's an unfold, then tests, unfolding, testing, unfolding, testing. So a lot of people will have very sleepless nights for a very, very long time until this thing is up and unfolded successfully. So radar signals are created here. They bounce off of that dish, hit the ground, come back to the radar, and then get recorded. And this is how we image the surface over time. A very, very large, a very exciting instrument. Sorry, I'm going to have to zoom again. So in addition to being a really beautiful instrument, it has some capabilities that are unique and will allow science better than any other instrument could do in the past. And if you indulge me for a minute, I'm going to try to get a little bit more technical. So one of the reasons why NISAR is cool, it uses a technology that's called synthetic aperture radar. What SAR does, it takes a sequence of images that we are taking the way it's shown on this animation. Each one of these images that we are taking is a fairly low resolution. But we mathematically combine all of these data sets together to achieve a data set in the end that has very high resolution. If you look on the top right of this figure up here, you may see how this image that we are creating is getting more and more detailed as the acquisition goes along. Hopefully you can see this. It starts out, when it sort of restarts the animation, it starts out a little bit washed out and then gets more and more fine-grained. And apparently the animation played only once. Twice. Did it play twice? Let me do this again. Sorry about that. So focus on this top right corner here. You should see initially that it looks fairly blurry. As we collect more and more data, the data set becomes more and more fine-grained. And so NISAR is using a particular method that is called SweepSAR, which was developed for that mission, and that allows NISAR to create very high-resolution data sets down to the 3-meter resolution over a very wide swath of about 240 kilometers. So a very, very large data set covering a very large area at very high resolution. This is one reason why NISAR is great. It's creating this global coverage of high-resolution data. But additionally, it does that using a very specific flavor of microwave signals. It uses a wavelength range that we call L-band. And it's different from some of the systems that are out there right now. The systems that we currently are using a lot, they are operating at C-band over here. And C-band cannot penetrate through canopies, cannot penetrate through tree covers very much. But L-band has ability to penetrate deep into the vegetation and hit the ground underneath the vegetation as well. And that penetration allows NISAR to see things that we just cannot see and do things that we just cannot do with other systems. For instance, if we penetrate into a tree deep enough, we actually gain the ability to characterize that tree. We can measure its biomass, we can measure its vegetation and crown structure and so on, which we can't do with other sensors. And additionally, once we penetrate all the way through, we can also see things that are happening underneath the vegetation cover. And an example of that is shown here. This is from a Japanese satellite that was flying in the 90s just to demonstrate what NISAR will be able to do. What you see here in the top left is an area in the Brazilian rainforest now. During the dry season, you see the trees above and you see the forest floor beneath it. This area gets seasonally flooded. It's next to a river that floods very extensively left and right every season. And this flooding, because it's under trees, is otherwise not observable. The L-band data from NISAR will be able to show as a marked difference in these very bright colors, all the areas that are flooded where there's flooding under the trees. So inundation under vegetation covers is something that NISAR can see that an optical system and even the current radar systems cannot tell you. It's a new hazard, a way of mapping hazards that we didn't have available before. So staying a little bit technical for another minute to sort of show you somewhat or talk to you about some of the superlatives of NISAR. One of them is, while we've built radars for a while, all the radars that are currently in space, they only support one wavelength. For instance, a C-band or an L-band type radar. NISAR is going to be the first one that is operating two different radars on the spacecraft. One in L-band. The L-band radar is being provided by JPL, by the Jet Propulsion Laboratory, was built there. And it will provide global coverage. It will measure everything around the planet every 12 days. Then there's an additional S-band instrument. This instrument was developed and built by the Indian Space Research Organization. And it will provide coverage over some areas like in India, all of India, the Hindu Kush Himalaya, and some parts in the United States. And so for those places, we have both of those available, which will unlock some science that we couldn't just do with a single sensor alone. Speaking more technical, NISAR will fly the largest data recorder ever flown on a spacecraft. Because NISAR is going to create so much data, we needed to build new technology to be able to store and communicate that data to the ground. So it's the largest data recorder. Additionally, NISAR is conceived in a way that it has the largest duty cycle. Does anybody know what the duty cycle of a satellite is? Has anybody heard this before? It basically tells us if, when the satellite revolves around the planet, it takes it about 90 days to go once around the planet. The duty cycle tells us what percentage of time we can use of these 90 minutes for imaging. And for radars, it's very difficult to image for very long times because radar are active, they consume a lot of power, they create a lot of heat. But NISAR is designed so efficiently that we can achieve up to 70 minutes per orbit of on time. And those two things combined allow us to image the entire planet every 12 days in ascending and descending. So you'll get data twice, every point on Earth is going to be seen twice by NISAR within 12 days, and every acquisition is successful because it's all cloud-free and day and night capable. And lastly, I want to say that the data is free and open. This is not necessarily new for folks that are used to NASA data. NASA has adopted a free and open data policy for a while. But in the field of radar, that's a fairly new thing. There's a European sensor that's flying right now that provides free and open data. And NISAR will join that by making all the data it collects freely and openly available. And I want to emphasize again, the technology that's being built is built by a fantastic team of people at ISRO and at NASA. Folks at JPL, led by project scientist Paul Rosen and his team, have done a fantastic job of putting such a fantastic instrument together. So I have a couple more slides on technology, so stick with me just for a moment. Another thing that radar does that you can't get from an optical system is it provides much more than just an image. So everything we've looked at so far is the thing that you see here, is the image, which basically shows you how much energy is coming back from the ground, and you use that to form an image. But radar has a couple of additional things that we can do. We can create these images in what's called different polarizations, which means that we can create a microwave energy that is oscillating in different directions. We can create them in a way that the signal oscillates up-down or the signal oscillates left-right. This oscillation plane is called polarization, and the cool thing is that different polarizations interact with the ground differently. And the different polarizations allow us to say what is in our pixel, in our image pixel, whether it's mostly vegetation, mostly water, mostly buildings, etc. We can tell that from the polarization. So it's very useful for image classification. And lastly, radars intrinsically are really good at measuring distance. I mean, if you think of what you use radars for today, most of you have a radar in your car, for instance, that warns you of vehicles in front of you and measures the distance to those vehicles. So distance measurements is something we are really good at. And radar can use that to track at the centimeter accuracy the distance between the satellite and the ground. So if the ground would be moving for any reason, we can track that motion of the ground at the centimeter to even millimeter accuracy, which is a phenomenal thing that I'll show you some examples of that radar can do. And NISAR will be doing better than most other systems. And so the way we use the phase is what we do is we basically, NISAR will fly over the ground once every 12 days. It's going to repeat a previous orbit 12 days later. So we'll take an image the first time around, and then a second image when it comes back 12 days later. And then we look at the differences in these phase measurements, which tell us something about the difference in range. And so what we form is, we call those an interferogram. These are these like tie-dye shirt looking images that you see here. And you don't need to know too much about them. What you should know, though, is in places where you see lots of color change, this is where motion is happening on the ground. So in this case, this is the imprint of an earthquake. So an earthquake happened and moved the Earth by a few centimeters during the earthquake. And NISAR will be able to pick this up at the centimeter to millimeter accuracy. Another example of how this could look is if you think of a volcano. If you have a volcano and there's magma moving into a magma chamber underneath the volcano, this increases the pressure under the surface, which propagates up, and the volcano will slightly uplift this way. And the more the volcano uplifts, the more of these phase or color patterns we see, and we can use those color patterns to not only identify where motion is, but also quantify, again, at the centimeter accuracy, how much motion happened on the ground. And then we can connect that to models to understand what is the physics underneath the surface. So NISAR's observations will allow us to understand dynamics in the subsurface. So NISAR, with all of this capability, is going to support a range of different science disciplines. In fact, NISAR was built based on requirements that mostly came from 3 different science disciplines that I want to briefly introduce. So requirements came from the solid earth science community. So these are folks that are dealing with volcanoes, so these volcanologists. It's the seismologists that are trying to understand how earthquakes work and how energy is released during earthquakes. But it also includes folks that work on landslides, that try to understand hydrology, how aquifers react when they get depleted, or folks that are interested in monitoring hydrocarbon extraction, for instance, including folks that work with the oil industry on monitoring their resources. Requirements also came from the cryospheric science community. NISAR will provide data for the cryosphere, monitoring all the global ice masses. And so we want to understand the dynamics of sea ice, which you see on the top, but also the movement and dynamics of the large ice sheets. So the ice sheets and the glaciers. So also those provided requirements. And the third community that NISAR will feed is the ecoscience community. And so there we'll use the polarization that I mentioned earlier today, and that will allow NISAR to quantify things like biomass, above ground biomass on a global scale, and changes of biomass through either deforestation, through diseases in forests and ecosystems, or through regrowth. We will be using it to map agriculture extent, do agriculture classification, and look at wetlands and changes in wetland extent. But in addition to that, NISAR will have applications for a number of much more hands-on kinds of things. Its data sets will be useful for looking at fire scars and monitoring how fires progress. It will be useful for looking at flooding. I'm going to show you an example later. SAR is actually really good at measuring the extent of surface water, and through NISAR will be even better because it also can see water under vegetation. And lastly, we can look at things like marine hazards, such as oil spills, biogenic slicks, storms, wind speeds on oceans. So it has a very, very wide range of applications. To show you some examples of the three main science disciplines that we support, I want to start with the solid earth geophysics. This is an example that I received from a colleague of mine from Caltech. Mark Simons and his team worked on this work. And so what you're seeing here is aquifer depletion under the Los Angeles Valley. And so NISAR can measure subsidence related to aquifer depletion at the millimeter scale as a function of time. And what you see here on the left-hand side is the secular, sort of the long-term change of the surface as the aquifers under Los Angeles get over-depleted over time. So you see Los Angeles over this time frame has subsided by about 5 centimeters because of more water got extracted from the aquifers that came flowing back in during rainfalls. On top of this, on the left-hand side, you see seasonal signals that are also present. As rainfall patterns change, in the winter you have more precipitation and the aquifers partly refill. And in the summer, when it's drier, the aquifers get depleted. And you see all of these dynamics, again, at scales. I don't know if you can see the scales here. This is plus minus 2.5 centimeters measured from a distance of about 800 kilometers in space. It's a capability that's almost mind-blowing to believe, but has been used now for a number of years. For the cryospheric community, NISAR's goal is to measure the dynamics of all ice masses on Earth, sort of a global understanding of the dynamics of all the ice masses. This example comes from Ian Jockin. He is a professor at the University of Washington. He's part of the NISAR science team. And so his work, for instance, looks at the ice dynamics of Greenland. And the way NISAR will observe these ice dynamics is it will measure the motion of ice in two different directions when it flies in sort of ascending direction. So when it comes up from the equator up to the pole, it gets one view on the ice cap. And then when it comes back down on the other side from the pole down to the equator, it gets a second view on the ice cap and gets a second measurement. With those two measurements, we can resolve two dimensions of the three-dimensional ice velocity. And then with some additional assumptions, we can come up with maps like this, which show us the absolute speed or velocity that the glacier, in this case, the Greenland ice cap is undergoing. And you can see that these blue areas here, those are where the fastest ice motion is happening. This is where the outlet glaciers are feeding into the ocean. And so ice is being transported here from the ice divide, which is sort of this reddish spine that you see here in Greenland, toward the ocean on this side and on this side with certain velocities. And NISAR, because we get data every 12 days, we can't only get global Greenland or large-scale Greenland coverage once. We can get these data sets every 12 days. And so what NISAR will help to do is get ice velocities as a function of time. And so this is what this data set could look like. This is from a fantastic project from a guy called Alex Gardner. He's a glaciologist from JPL. He's running a project right now that uses all Earth observation data since the 1970s, the Landsats and the different SAR missions since then, to get a long time series of velocity for all glaciers on the planet. Very, very ambitious project that we are very happy to be a part of. And so one example that's shown here is Malaspina Glacier. Hopefully you may have seen that on a map before, or have been there maybe even, or flown over it. It's in a glacier in southeastern Alaska, very, very beautiful glacier from top. The map here on the left in color shows you the velocity. This is the average velocity of the glacier, color-coded, so that the purpley colors are the faster motions, and then the bluish and green colors are slower motions. But then behind each one of these 3 points that I picked out, we have a full time series of ice motion going all the way back to the 70s. Thousands of measurements over time of detailed information how the ice motion is changing. And you see some patterns here. For all 3 of those points, you see seasonality, which makes sense. The glacier speeds up a bit in the summer when there's melt and more water supply for the glacier, and then slows down in the winter. And then some glaciers do funny things. Malaspina, if you may know this, is what's called a surging glacier. It has these episodes where it suddenly speeds up and transports much more ice to the ocean. And it went through one of those episodes starting in 2020 and has since, I think, subsided back to its normal velocity. But it's the kind of information that NISAR will be able to provide for every glacier on the planet. For ecosystems, I mentioned earlier that one of the things we do with ecosystems is look at biomass and biomass change on a global scale. This map is created from SAR sensors in collaboration with some LiDAR data sets. It was provided by Sasan Sachi from JPL. This shows you biomass estimates in South America. It turns out most of the above-ground biomass on Earth is located along the equatorial belt, in the big rainforests around the equatorial belt. And so where most of the biomass is actually located is where we have the least information, because cloud cover over this area makes it really difficult to measure biomass consistently. So NISAR, with its cloud penetrating capabilities, will help us improve our knowledge of the global biomass, above ground biomass, a great deal, and then also help us understand how that biomass is changing over time. So before I go back and bring this all back to Alaska, one more first that NISAR has brought that has made our life quite different and has impacted a lot of what we're doing to support NISAR here in the state. NISAR is providing unprecedented data volumes. So NISAR and it's doing that because it provides literally data everywhere. It's a mission that does, as I mentioned a few times already, has this global coverage goal and will provide global coverage every 12 days. This map shows the coverage that we're providing, all the land masses on the planet. The color coding here is roughly the dark green color over North America is a mode that will provide roughly about 5 meters spatial resolution for all of North America every 12 days. The light green color is a slightly lower resolution mode that we'll dedicate for the rest of the planet. That's going to be about more 7 to 8 meters type resolution. We have these purpley modes are interesting. Those are the places where both the L-band, I mentioned earlier that it's 2 frequencies, both the L-band and the S-band are operating together. So these are the places where you can experiment with this new dual frequency data sets. It's done all over India, in the Hindu Kush Himalayas, sort of the Himalaya mountains, some parts of the Antarctic, as well as some selected places in North America. The yellow regions are the ice modes, the land ice modes. That's actually the highest resolution places that we'll get. There we operate the instrument at the full capability of about 3 meters spatial resolution. We need that resolution because the dynamics of land ice are very high. The motions that we are seeing there are very high. and we need the highest resolution to measure that accurately. And then lastly, we have in red the sea ice mode. This is a slightly lower resolution mode, 10-ish meters resolution that will allow us to understand the extent of ice, help us with ice classification, and understand the dynamics of sea ice. And again, the different layers that you see here in the back, they indicate that we'll have these data every 12 days in ascending and descending direction. So all of these acquisitions at super high resolution together will create an enormous amount of data. So NISAR will produce an amazing 50 petabytes of data per year. Currently, NISAR is formally funded by Congress for a 3-year mission lifetime. It will last much longer than that, but that's currently the funded lifespan. Over those 3 years, it's going to create 150 petabytes of data. Does anybody have any feeling what a petabyte means? Does anybody have hard drives that are a petabyte? Do you have any idea? So it's very difficult to understand what that means, but just I give you 2 data points. One is NISAR in its 3 years will provide more data in only these 3 years than NASA currently holds in all of its archives combined. So it's going to double the amount of data in NASA's data centers with one mission. That's one data point. Another one, a bit more comical, that I tried to do is like, is there something more relatable? So if you were to convert NISAR into 4K high-resolution movies, you would take about 1.6 million movies, and it would take you a little more than 400 years of nonstop watching to get through all of those. So that will make the Super Bowl look really short compared to that. So it's an enormous amount of data that will keep the science community busy for many, many years. Before I go to Alaska, I want to do one quick thing, if you indulge me. I want to summarize all of this briefly for you and let the people speak that are actually building the mission. This is a 2.5-minute video that I would like to play real quick. You'll see the project scientist, Paul Rosen, talk a lot, who is one of the ones that has orchestrated a lot of the science disciplines and all the requirements around it. And you get to see actually the instrument as well. And it gives me a short break of not talking. So let's see if that plays.
With NISAR, we're tracking the changes of the solid Earth and how it's moving, ecosystems, ice cover, and any other thing that's changing at the scale of a centimeter on the Earth in a way that we've never been able to see before. Because of these very
awesome, doesn't it?
We can measure, we're able to understand what's happening below the surface of the Earth at great precision. We can see subsidence, and that allows us then to manage resources of what's happening below the Earth.
Scientists want to study the movements of the Earth's surface to understand the processes that could trigger earthquakes, volcanoes, and landslides.
And that allows us then to understand risks associated with natural hazards,
which in turn can help in mitigation measures and early response. Other changes over the Earth's surface include melting of glaciers and ice sheets, changes in forest biomass, soil moisture, and shoreline changes.
It's based on radar, so it has 2 different frequency radars, and it basically looks through clouds and sees the surface of the Earth. What you're seeing is an animation of how the radar collects data, and you can see these beams coming down from the antenna and coming back, and on the ground you can see the swath, and that's where it collects the data, and when it combines them all together, you get what we need for the science.
We can see day and night through clouds, and we're covering all of the land and all of the ice-covered surfaces of Earth every week. NISAR is quite unique in that it has 2 radars, one provided by NASA, one provided by ISRO, the Indian Space Research Organization.
NASA and ISRO have collaborated in this mission. Till last year we were there at JPL, NASA, where the radars got integrated and tested and were shipped back to India. And now the spacecraft is getting integrated with the instruments.
This is a fantastic thing. Let me talk about this later.
NISAR is going to be launched from Sriharikota, which is a ISRO launch pad, and it is going to be launched by GSLV Mark II. So we are just looking forward for the launch of NISAR in the forthcoming year.
NISAR is measuring the changes on the Earth's surface, which are either factors or indicators of climate change. The society will also immensely benefit due to its contribution towards disaster management and providing food and water security.
These things are global problems that the global community needs to come together to resolve.
Now it looks like we are no more belonging to two different worlds, and we all belong to the space community. That's it.
There's the excitement about what we are going to learn that we didn't even anticipate we were going to learn.
So you saw that large chamber that they have that they put NISAR into. It's a huge vacuum chamber that they use for thermal testing. So they crank the heat up to sort of simulate very high temperatures in space and then make it really cold to simulate really cold temperatures in space. It's an amazing facility. And you could also double check me in this video, so hopefully you saw consistency between what I said and what they said in the video. So at the very end, I want to say, like, why am I talking about this? What is Alaska's role in all of this? And it turns out Alaska's role in NISAR is pretty large. We have been working with JPL and ISRO on NISAR for many, many years. And specifically involved are folks at the university here, especially the Alaska Satellite Facility. So Wade is the director of ASF. ASF is NASA's data center for radar remote sensing data. So the types of data that NISAR will bring, all of the historic data that are available that NASA owns or has contracted out are all managed by ASF, by us, and made available to the community. In addition to the data center, ASF also does something else. You may recognize this thing on top of the Geophysical Institute, the dishes that you see around campus. Those are dishes that ASF is maintaining. So we provide space communication for NASA. We are part of NASA's Near Space Network. And so we do uplink to satellites to update commands and status of these satellites. But we also downlink data for I think currently about 12 or 13 different NASA instruments directly here to Fairbanks. And so we will play and have been playing a very large role in NISAR. We've been collaborating and working with JPL for a long time. And within NISAR, we'll meet 4 different responsibilities. We will be a communication ground station. So we'll downlink a lot of the NISAR data sets directly here to the interior of Alaska from the spacecraft directly. We will be the archive of NISAR. So these 150, those like 1.6 million videos, all of those we will manage, make available to the community, we'll distribute the data, and we've built a lot of services around it that makes it easier for folks to harness that data volume. Accessing that amount of data is really hard, and so we've spent a lot of time trying to make that data accessible. And we also have tried to come up with ways and services that make this quite complex, dense data set more digestible for folks that are not experts. So that's sort of what we've been up to for the last few years. Speaking to both of the pieces, so ASF is supporting NISAR with all 3 of its pieces. ASF has currently about 95 employees that are sort of spread among 3 different components. One of this, the data center, this is where the NISAR data will reside, so that manages all of the NISAR data set. We have the ASF ground station, which will provide the space communication. And then we have a 3rd piece that we call ASF Enterprise. That's a thing that lets us bring in other funding outside of NASA to do other new cool things. And through Enterprise, we've been developing a lot of services and a lot of tools that make data sets like NISAR more digestible. Regarding the amounts of data that NISAR will bring, it has actually changed the way NASA is doing business. The data volumes were so daunting, it required NASA to move all of its data centers into the cloud. In ASF here in the center of Fairbanks, we have been helping lead NASA into the cloud. And so we have been trailblazers and one of the leaders in cloud development within NASA. So it's a skill set we have here in the state that you can't necessarily find in many other places. In terms of the ground station, ASF is very important, or Alaska is very important for NISAR because of its high latitude location. NISAR, like many other Earth observation missions, they are what's called polar orbiting. So they come over the pole every time, and orbits get closer the closer you get to the pole. So we in Alaska can see a satellite just more often than they can in the lower 48. For NISAR, for instance, NISAR will go around the planet about 16 times every day, and I think we can see 12 or 13 of those orbits from ASF, which is much more than we can do in the lower 48. This makes Fairbanks a very important hub for Earth observation and for organizations like NASA. And it's really why ASF is here in Fairbanks in the first place. Also, for ground stations, NASA had to redo business or change their business because of NISAR. NISAR's data rates are so high that we actually had to upgrade a lot of the ground station equipment to be able to keep up with the amount of data that's coming down from NISAR. As part of this, we in ASF, we in Fairbanks actually got a brand new antenna. That one's actually not located on campus. It's about halfway out or 2/3 out toward North Pole. So if next time you drive to North Pole, look to the right-hand side, about 2/3 down, you see a large radome. And in that radome is that dish hidden, which is a dish dedicated for NISAR and has capabilities that can keep up with NISAR's data rate. Outside of ASF itself, UAF has been participating in the development of NISAR for many years. I personally have been on the NISAR science team since 2012 and have been able and privileged to sort of influence the design of the mission, help make the requirements, develop sort of the processing methods, and do the validation for all that NISAR is doing. This image is from one of our science team meetings we had, I think, a couple of years ago at JPL. Everybody's quite excited because we were finally moving toward launch. And if you can't see me, I'm lurking here in the back. We do a lot of support for NISAR by developing science algorithms. We have been working on developing methods to do things like permafrost observations. We are actually providing validation support for NISAR for permafrost. I told you earlier that the radar signals can see the ground go up and down. And in permafrost sites, when you have annual freeze and thaw processes, you have an up and down of the surface also. And we can look at how the ground is subsiding and can convert that to information about how much ice is there stored in the active layer in the permafrost underneath. So we can compute what's called excess ice content. And on the bottom, you see a map here. This is from northwestern Alaska. The sort of yellowish and lighter red colors, those are places where there's lots of excess ice content in the ground. And why this is important from a practical perspective is in places where there's lots of excess ice content, if temperatures keep going up, it means that this ice is going to melt out and the ground is becoming unstable and will collapse over time. So these are places where you don't necessarily want to build your house in the future. So that's something that is very relevant for future infrastructure activities in the state. We have developed lots of technology to do flood mapping, automatic flood mapping from SAR. SAR is really good at monitoring water extents. We prototyped this initially for the 2015 Sag River flooding that many of you may still remember. There was at least 2, I think, disaster declarations for that. And so we provided information on the water extent as a function of time. So here the different colors mean that the more yellowish colors are where the water was early during the event, and then later in the event are the sort of darker red colors in this plot. And so we've since been getting funded by NASA several times to operationalize this service. And one of the things we do right now is we provide automatic flood monitoring throughout the Hindu Kush Himalaya. So we support the countries of Bangladesh, Nepal, India, and Bhutan with regular flood observations from SAR. They get affected every year by very heavy monsoon flooding, and so we help them manage these flood hazards. And lastly, if you were at the talk last week, folks talked about the Edgecumbe volcano. which is an interesting volcano in the southeast near Sitka, which was considered to be dormant, but then showed signs of life starting 2 years ago. And the way we discovered that there was life was partly through SAR and through its capability to do surface displacement. So this is courtesy of Ronnie Grappenthien, professor of geophysics at UAF, who with his grad students used thousands of SAR data sets to measure not only how much Edgecombe is deforming, but also when this episode of recent deformation started. And so we've been working with the Alaska Volcano Observatory and Ronnie's team for the last few years to integrate all these SAR data sets into their operational hazard management systems. I have 2 more slides, I'm almost done. So a passion of mine is making sure that people know how to use these data sets. So we've been doing lots of education and training for how to work with NISAR data sets and SAR data sets in general over the years. Since 2018, we have basically been training pretty much on every continent. We've been to South America, Central America, Eastern and Western Africa, several places in Europe, several times to the Hindu Kush Himalaya and Asia. And so we've done in-person trainings in all of these places. We have developed curricula for university classes. We have done webinars. We have online trainings that are available in webinars that we've done over the years. So lots of work to make sure that people know how to use the data. And at the very end, I want to bring this back also to the team at the university and at the Alaska Satellite Facility. It's sort of a part of the story for me that's very important and very gratifying for me, but doesn't necessarily always get a lot of attention. The folks that have been making NISAR reality here in Alaska, that built all of the pipelines that you will be able to use when you want to use these data sets, a lot of them are homegrown. They are either from Alaska or came to Alaska to attend UAF, that went through the UAF system. They started working with us as undergraduate students, as interns, and then stuck around and became part of the team. And so all of the names on here are people that we just hired since 2016 to help us out build all the infrastructure behind NISAR. And it's sort of a nice and gratifying story from my end to sort of show that we are able to, that we're interesting and attractive enough to bring in talent and keep talent in the state. And I want to say that these people they're really the backbone of everything we've been doing. The folks that we've hired from the state are shining through their ingenuity, their creativity, their skill set, of course, but also their just ability to work in teams. It has been really fantastic to see these people come in and grow over the last few years. And with that, I want to end the story about NISAR. Currently, the launch date is April 25th. So set your calendars, mark your calendars for the launch. Hopefully, it's going to stick for now. We'll see. We'll let you know if it changes. But we are all super excited to see this thing lift off and go into space and provide data for generations to come. And I want to thank you all for your attention.
All right, thank you, Franz. So now we can move into some audience questions from both our in-person attendees and those online, of which we had 88 people tuning in, which is great. And just a quick note, although some of you may be able to easily project your questions loud enough to be heard in the auditorium, we ask that you use the microphone so our online viewers can hear your questions as well. For those of you joining virtually, you can type your questions and we will read them aloud. So any questions from the in-person audience?
Oh, don't hurt yourself.
Okay. So how much data does NISAR buffer on the satellite, and then how does it get it down during the window of opportunity going over an antenna?
Yeah, so I know it's the largest data recorder ever built. I don't know off the top of my head how large it is. We will be filling it up pretty close as it goes from one contact point to the next. So the locations that we have, do you know off the top of your head? It's Fairbanks, it's Punta Arenas, Svalbard, and Wallops in the United States. And I think there are Indian stations also for some of the Indian data sets. So it is pretty close to the brink. So there is what they call margin for margin of error if a station goes down, but we are maxing out the capabilities pretty closely. I'm not sure if I answered your question because I don't know exactly how much is on the onboard recorder.
I have another question. Help me calibrate how many terabytes in a petabyte?
How many terabytes in a petabyte? So let's see, terabytes to, it's 1,024 terabytes in a petabyte.
All right, any other questions from in person? Oh, one right here.
So soon you'll have a little thumb drive on your keychain that's a petabyte.
So in order to detect change, the satellite would have to know its own position. And how does it do that?
Yeah, it's a good question. It's actually quite amazing how good these orbit predictions are these days. It gets predicted orbits from teams that are doing orbit dynamics based on our knowledge of the gravity field, our knowledge of sort of past orbit points. We can predict the orbit pretty accurately. And then in addition to that, it has GPS, GNSS systems, so navigation systems on board that are also tracking the orbit over time. It uses things like star trackers to understand what its orientation is, little gyros on board to track its attitude and its location over time. And so these data sets are actually downloaded with all of the other stuff that comes down. And so there's going to be an initial predicted orbit that's already quite good at sort of the 10, maybe few centimeters level. And then with all the data that comes down, they will recompute the orbit and provide what's called a precise orbit, I think a few days after the data collect. That will make the orbit information even better. And it's all done using orbit dynamics and all of the information we have available now about the shape of the instrument. You actually need to know things like, what's its drag in the atmosphere. Even though it flies at high altitudes, there's residual atmosphere that drags on it. There's wind coming in from the sun that needs to all be calculated. But these days, orbit dynamics is a very mature discipline.
I was wondering what type of information the S-band provides that the L-band does not, and how much power consumption do the solar panels provide for all the onboard equipment?
Right, so S-band is, so I didn't mention the wavelengths too much. L-band, one thing I like about radar overall is that the wavelengths are something that you can very nicely visualize. If you think of visual light, like, I don't know, red light is what, like 700 nanometers? Nobody knows what that is. But an L-band radar has a wavelength of about 25 centimeters. That's, you can point, you can hold up your hands and people understand. And so L-band is about 25 centimeters. S-band is about half of that. It's about 12 and a half or so centimeters. So it's going to have different penetration into vegetation covers. It's going to respond to soil moisture variations differently. And it's going to scatter off of the ground slightly differently. It turns out that for some reason we haven't really used S-band much on planet Earth for no really apparent reason. It's actually a very popular band overall. It's been used for a lot of space missions. Who is familiar with Magellan? Does anybody remember the Magellan mission? It was a mission to Venus and mapped Venus. It was a radar that operated at S-band. And so a lot of the space missions use S-band, but on Earth we haven't done that much. So I think we'll learn a lot about what the value is that S-band is going to bring in addition to the bands that we've been traditionally using.
One more question over here.
Oh, I forgot the solar panel question. So the solar panels on NISAR are very large and provide a lot of power. And so that also enables both of the instruments to be on for a very long time. So the power consumption and the heat budget are what defines how long the radar can run. And both of those are quite efficient. They're actually more efficient with the L-band. The L-band on the instrument is slightly better located physically. For instance, the way you get rid of heat is you have a radiator that points into deep space. So you want to point it towards something that's really cold. And so the L-band heat radiator points into deep space, which has like 3 Kelvin, very cold temperature. The S-band, unfortunately, points closer to the surface of Earth and has more background heat, and therefore is not quite as efficient. And so the S-band can't run quite as long as the L-band does.
All right, we're going to do one more question in the room because we have several very interesting questions on Zoom.
Hi, you said you're doing a lot of like cloud development. So for that, are you using any commercial available solutions such as AWS or Azure, or going with something more open source?
Right. So NASA has, for now, decided on AWS, Amazon Web Services, as the cloud vendor to store all of its data sets. The development that we've done in AWS is, though, ideally in a way that we can move if we have to. So we're not locked in to AWS in that particular sense, but for now, AWS is the vendor that NASA is using. And within AWS, NASA has developed a system that's called Earth Data Cloud, which is somewhat a secure space within AWS where they can make sure that the data sets are safe and maintained. So for now, everything's in AWS.
All right, moving on to our online questions. Question from Jim on Zoom, which may relate to what you were just saying, Franz. Seems that this could be used for military purposes. How can the military be kept out?
A very interesting question. So it's actually very interesting because we were at a conference last December where one of the questions was similar, where somebody working for the military said, like, well, if we have this maneuver, how can we make sure that you don't release this data set? The data are freely and openly available for everybody. The reason why we are not super concerned about military applications is because the military has their own radar systems. And they have systems that are higher resolution than what NISAR will provide. And therefore, for the really critical applications, I think NISAR doesn't have a super interesting applicability. But it's going to provide a lot of context for, that's also, potentially interesting for mapping, military mapping activities. Can we keep the military out? Data sets are freely and openly available. The good part is if the military uses the data, everybody else can too. So there's no particular secrets that only the military would have, if that's the concern.
All right, this is from Sebastian on Zoom. Greetings from Mexico City.
Okay.
In addition to the development of the satellite platform, will specialized software be developed for SAR image processing, or will it be integrated with existing software such as SNAP? Thank you for sharing your knowledge.
Yeah, very good point, and one that we didn't actually talk a lot about. NASA has put out a mandate for open source development. So the codes, the processing codes behind NISAR, all of them will be and are already publicly available. JPL is embedding them all in a software package that they are releasing that's called ICE. Stands for Interferometric Scientific Compute Environment. And I'm very proud of myself right now. And so you can send me an email there. My email is on the screen if you want a link to the GitHub repository, but all the codes are on public GitHub. Everything that we do at ASF to process the data into scientific products, into analyzed data sets over time, all of those codes are also freely available. They're all in free and open Python, and they're all available in open Git repositories. So you can use the codes, but you can also contribute, which is actually something that we are really keen on seeing the community do, develop new toys and then donate them back to the community so that we can grow an ecosystem of tools around the data. Good question.
All right, from Brian on Zoom, amazing technology, but I'm easily confused, so please expound on the spatial resolution, which you have variously described as 3 to 5 to 7 to 8 to 10 meters versus centimeters or millimeters elsewhere in the talk. What did I miss?
Yes. So the spatial resolution, which is sort of, if you want, how close things are on the ground so that you can still see them as two different things. NISAR has a variety of different modes that all provide slightly different resolutions, but on average you can bracket it with sort of the 3 to 10 meter resolution, depending on what mode is being used. It actually, if you think that's complicated, it's actually more complicated than that, because originally SAR has this strange habit that the resolution in one image direction and the resolution in the other is actually not the same. So I'll spare you that. But it's going to be a 3 to 10 meter resolution in the end. The millimeter thing is separate. The size of the pixel is about 10 meters, but then the accuracy with which we can see that pixel move up and down, that is at the centimeter scale. So we can see if, the place I'm standing, if that's the pixel, if I sink in because I ate too much pizza over the last few days, I could measure that sinking at the centimeter to millimeter quality. And centimeter to millimeter, because it depends on how many data sets I use. If I use a single one, it's at the centimeter scale. If the motion is consistent and I have 100 images, I can measure the rate of motion at the millimeter scale.
All right, and Brian has another question, which I also had. How susceptible is that large, fragile-looking dish structure to damage from space junk and meteoroids?
It's bulletproof. I'm not building those dishes, so if somebody from JPL is on, please don't send me hate mail. But I think it's pretty robust. The mesh, I think, is constructed in a way that it can withstand individual holes without rupturing. So it's tested technology. While this dish hasn't been used extensively for radar, it's been used in a lot of other space communication instruments before. So it's not something that isn't tested.
All right, question from Ketan on Zoom, and Ketan is a UAF grad student. Could we track ice content within frozen bedrock using NISAR?
Ice content within frozen bedrock. I have never thought about this. I would venture to say no. So NISAR has capability to penetrate into certain things, but what it can penetrate into it depends on really two things. Is first of all, how large is it? It can penetrate into vegetation mostly because you can think of the ratio between the object that's blocking the radar and the wavelength. If you think of a leaf that's about the size of your hand and you have a wavelength that's 25 centimeters, the wavelength is bigger than your hand. And that allows it to basically move around it and penetrate through it. If you have a big rock, it usually gets blocked by that rock and scattered by that rock. So we can't actually penetrate into it. What we can penetrate into are other things that are loose. We can penetrate really well into sand, for instance, and quite deep into dry sand, partly because it's dry and partly because sand in the end is just little crystals with lots of air in between. We can also penetrate really effectively into snow layers, like in the center of Greenland, which has deep layers of fairly unconsolidated snow. The NISAR signal will penetrate probably tens of meters into the snow layer before either it gets lost or it gets scattered from some inclusions. But for rocks, which will not be able to penetrate, we also cannot penetrate into water.
Just two more questions from our online folks. This is from Mike, can you map hotspots suitable for geothermal energy in interior Alaska?
That I may have to punt on, But again, I'm not an expert on geothermal energy, and I'm not entirely sure if there are things we can see from space that may help us pinpoint them. But I'm not saying that it's not possible. If you're really curious, send me an email to the email address on the slide, and I can try to connect you with somebody that may have a better answer for you. Sorry about that.
All right, and last one. This is from AM. On the slide with the world map of different data resolution areas, what did the light blue and pink areas represent?
Well, that is a fantastic question. Let me see. I'm bringing it up, just a second. Oh, here we go. So the light blue and pink. Okay, so the pink we have here, and then where is light blue? Oh, there's some light blue over here. Let's see, so the pink is a mode it's sort of an ice mode that's used by the Indian Space Research Organization. So that's using both L-band and S-band at what I believe is a slightly lower resolution, lower spatial resolution, but it's a joint mode. So the purple and pink ones, they are joint modes where we have both the L-band and S-band data available. The blue, I think, is urban targets. I bet it's calibration. Which one's the blue ones? The light blue, South America and Southern California. Yeah, it could be calibration sites or agriculture sites. I'm not entirely sure. But also there, you can email me and I can send you all the details about the different modes. I also have to confess that this map is slightly outdated. These modes have changed a little bit. I chose this one anyway because it's a little less complicated than the one we currently have. And when I say this seems complicated, but the big point is that whatever mode you get in your place, it's going to be the same mode consistently through time. And so every 12-day data set will look the exact same for you, whatever mode it is.
All right. Another round of applause for Franz. Thank you very much.